Yeah, so if we have a category and a coverage, we call such a category a site. And we have many examples of sites. For example, topological spaces with open covers form a site. So we assign to each object a family of all possible families which give open covers of this object. We have schemes with Zariski open covers. We have schemes with étale covers. We have manifolds with open covers. We have manifolds with good open covers, which means that an intersection of any two elements in this cover is either diffeomorphic to a ball or is empty. And finally, just some exotic example. We can take any pole set, consider it as a category, and give it an atomic topology, which means that we say that the subset is open if it consists of elements which are less or equal than a certain given element of a pole set. So, as you can see, there are many examples of sites. And the notion of a site is generally used to define sheaves. So obviously, for any category, we can define three sheaves. But in order to give some restrictive conditions which capture the geometry of this category, we impose additional condition known as descent condition or shift condition, which says that if we have a coverage, well, if we have such a covering family, which belongs to our coverage on this site, then we should have descent property, meaning that if we given a family of elements inside of each of these f of ui, and we have a pair of morphisms. So for any pair of morphisms like this, we have the pullback of this element. So the pullbacks of these elements coincide. So they pull back to the same element on V. Then there exists a unique element in f of u, such that when we pull back x along fi's, we get xi's. So that's just, in a sense, the usual shift condition that we can glue a section from restrictions to an open cover. But since we use these coverages, it's a bit trickier. Okay, and as I said before, we have a more common definition of a sheaf. If we assume that our category has pullbacks, then we can define a sheaf as such a pre-sheaf that it is isomorphic to the limit of the following diagram, so to an equalizer. We take a collection of these covering morphisms, then we take sort of intersections, but just pairwise pullbacks, and we have two morphisms which correspond to structure maps and the pullback. And in fact, this diagram can be extended, and we can consider triple intersections, etc. And we form a simplicial set like this. I'm sorry, in this case, since we're already dealing with sheaves, it's a co-simplicial object. So, and we require for this sheaf to be isomorphic to this co-simplicial object. But for sheaves of sets or sheaves valued in some discrete category, it's sort of a meaningless operation. We don't need this tail. It's just to give a more general picture. Okay, so now let's discuss lower Topoi. So we say that category S is a topos in the sense of Grothendieck if it is equivalent to a category of sheaves on a certain site. And Giraud's theorem, which is one of the fundamental theorems of topos theory, says that, in fact, this condition that some category is a Grothendieck topos is an internal one, meaning that if we have a category which satisfies suitable completeness conditions, it in fact can be realized as a topos, so as a Grothendieck topos. So we can find a certain site and a category of sheaves on this site would be equivalent to our category S. Okay, that's just some very general theory, but let's try to see some applications of this approach. So when it's beneficial to pass from individual objects in a category to the whole category. Well, for example, we can define something that is known as universal de Rham complex. So obviously, differential forms form a pre-sheaf on the category of manifolds. And the value of this pre-sheaf is tautologically given by just taking differential forms on a manifold. But actually, as you probably know, this pre-sheaf is a sheaf, meaning that we can glue differential forms over an open cover. But actually, we can deduce something from the fact that this is a sheaf on a category of manifolds. So first of all, since it is a sheaf and category of manifolds, it makes sense to take the values of this sheaf not only on manifolds, but actually on arbitrary sheaves. So we just take the internal home inside of, we just take the home inside of category of pre-sheaves from an arbitrary sheaf to our sheaf omega dot. And we obtain something which is actually an appropriate notion of de Rham complex for an arbitrary sheaf on manifolds. Why this is great? Well, for starters, we can consider the following situation. So assume that we have two manifolds of positive dimension. Then we can consider a sheaf on the category of manifolds, which is defined by this equation. So this is what is known as an internal home in a pre-sheaf category. So we consider this pre-sheaf, which is actually a sheaf, whose value on any manifold M is equal to the set of smooth maps from the product M times X to Y. And if we think of this sheaf conventionally, meaning that we try to introduce some kind of topology, try to think of it as a manifold, it's obviously infinite dimensional. Even if we have two one-dimensional manifolds here and here, we will obtain something infinite dimension. However, we can still compute the de Rham complex of this infinite dimensional manifold, even though topologically or differentially, in the sense of the usual differential geometry, it is quite painful to define anything for infinite dimensional manifolds. So, for example, if you try to, I don't know, learn Lie theory for Fréchet groups, it's horrible. You don't have an exponential map. You don't have the good properties of Lie groups you're used to. However, here we can still do all the differential geometry without any of the topology. And that's what's great about this general approach through Topoi. So we consider the Topoi of sheaves on manifolds with this open topology, and we can define our usual differential geometric objects like differential forms. Okay, and even more, we can define the universal de Rham complex, for example, for this sheaf of one forms. So we just take differential forms of differential forms. And as it turns out, this complex is isomorphic to this one, which is actually quite remarkable because usually the Rham complex is infinite dimensional in each degree. However, here we can see that it is finite dimensional for this universal sheaf of differential forms. And moreover, we have a canonical form inside of one forms on one forms, which corresponds just to the identity map. And even better, this one form is universal, meaning that if we have an arbitrary one form on an arbitrary manifold, we can pull it back and obtain this, we can pull back this universal form on one forms and obtain this differential form. So another good thing, we can explicitly describe how this de Rham complex of differential forms, so this universal de-Rham complex, is constructed. So we just, for even degrees, we just need to take the differential of this universal one form to the q's external degree. And for odd dimensions, we just need to take the wedge product of this universal one form with its external derivative to the power q. And that's another remarkable thing, that if we have some factorial way to construct an n form from, for example, one form, we can pull back this construction of an n form to an arbitrary manifold. So we obtain a factorial way of constructing n forms from one forms, or we can do it for any and m, and obtain m forms from n forms in this fashion. And this construction works for any manifold, since we're doing it for the universal de-Rham complex. So that's what sheaves can give us. But there are geometric situations where sheaves, in our usual sense, are not enough. So let's consider a common differential geometric situation. Assume that we have a principal bundle over M, where M is some manifold and G is some finite dimensional Lie group. Then we have, well, we say that we have a connection on this principal bundle if we have this one form valued in the Lie group of our group. And we say that it is a connection if, when we restrict it to any of the fibers, we get the canonical Maurer-Cartan form on G. So it's Maurer-Cartan form on G because since it's a principal bundle, each fiber is diffeomorphic to G. And additionally, we require that for any element G small in our group G, the right action of this element, so we just shift our principal bundle by G, acts on this connection as the adjoint action which is induced on the Lie algebra. So under these two conditions, we say that we have a connection on the principal bundle. And what we want to do? Well, it would be nice to be able to classify not just principal bundles, because we know how to classify principal bundles. We just need to take homotopy classes of maps from a manifold to the classifying space of the group G. And this thing classifies principal G bundles. But we want to classify principal G bundles with connection. So it's a bit harder. We have to keep track of an extra bit, because obviously we can have bundles which are isomorphic as principal bundles, but non-isomorphic as principal bundles with connection. And as it turns out, we can do this with just sheaves. We will need some higher structures which will eventually lead us to higher Topoi. Okay, so let's formulate the problem. We want to find some universal bundle with connection such that for any principal bundle with connection, we would have a unique morphism from M to this classifying something, such that this universal bundle pulls back to our bundle, and this universal connection pulls back to our connection. So that's the problem, and it seems like a logical extension of the usual problem of classifying principal bundles. Okay, so let's think. What would be the problem if we just try to use sheaves? Well, we can try the naive approach. So we define a pre-sheaf on the category of manifolds, which gives the following. So if we take a manifold M, then it gives us all principal bundles with structure group G over M and connection theta up to an isomorphism. And what is an isomorphism of principal bundles with connection? Well, it's quite natural. We just take something which is an isomorphism over M, so it covers the identity map on M. And if we take the form, the connection on P prime, it should pull back to the connection on P. So F is a pre-sheaf, and I mean, it's quite straightforward. We just take an arbitrary map, and the value of this pre-sheaf on this map is just the pullback of everything. And since the pullback is functorial, this is indeed a pre-sheaf, but it is not a sheaf. Let's see why. So first of all, let's consider the following simple manifolds. It's just a circle covered by the usual charts of the one-dimensional projective space. So we just poke out 2 points and take the complements of each point. And this complement is diffeomorphic to an interval. So we have the presentation of S1 as a colimit, in the following simple diagram. And we can apply our pre-sheaf to this diagram. For it to be a sheaf, we need this diagram to become a Cartesian square. But is it a Cartesian square? Well, obviously, if we have a bundle over an interval, it trivializes. So up to an isomorphism, we have only one bundle with connection over an interval. And if we have a disjoint union of 2 intervals, we have 2 different bundles over this disjoint union. But what is the value of this pre-sheaf on our circle? Well, as it turns out, the value of this pre-sheaf on our circle is the set of all conjugate DC classes inside of G. So it's orbits of the group G, which acts on itself by the conjugation action. So since G bundles with connection over S1 are uniquely determined by its holonomic conjugacy class, this is true. And obviously, the set of conjugacy classes in a Lie group is not the same as this pullback. So we have a problem. It's not a sheaf. However, there is a way to fix things, but let's first understand what went wrong. So why isn't it a sheaf? So as it turns out, connections can have non-trivial automorphisms. And when we do ordinary sheaves valued in sets, we don't track automorphisms. And the natural question is, what structure does track automorphisms? Well, as it turns out, the natural way to understand such problems is by considering groupoids. So let's start with a very simple situation. Say that we want to classify principal bundles with discrete structure group. So we don't have any Lie algebra. Our connection is always trivial. Even better, we want to classify just principal bundles with structure group Z mod 2. Clearly, such principal bundles are just 2 sheeted covers of a manifold. And if we have a 2 sheeted cover, we can actually associate to it a one-dimensional real vector bundle. So we can think of elements of the fiber as points of norm 1 on the line. And we can associate to a 2-sheeted cover a vector bundle. So through each point passes a line. And we know how to classify line bundles up to an isomorphism. Obviously, we can recover a 2-sheeted cover from a line bundle. We just need to take a line bundle, take an elements of norm 1 in each fiber, and we obtain a 2-sheeted cover. So we indeed have an equivalence. And we know how to classify vector bundles, one-dimensional vector bundles up to isomorphism. We just need to take the set of homotopy classes from M to the infinite dimensional projective space, which, as we know, is equal to first cohomology group of M with coefficients in group Z mod 2. But is it enough for us? Well, no, because isomorphisms of line bundles kill too much information. For example, we kill the information about reversing orientation. And Therefore, we kill the information about a non-trivial automorphism of a two-sheeted cover, which just flips the points in the fiber. So we need something more intricate than just this homotopical classification. And we can do that. We can define a groupoid which is associated with this two-sheeted cover. So assume that G is a discrete group, meaning that we don't have to care about the connection. Then we define a groupoid with objects given just by all principal bundles over a given manifold. So it's the value of this groupoid on a given manifold. And morphisms are just isomorphisms of principal bundles which cover the identity morphism in M. Then we obtain a functor, a presheaf from manifolds to groupoids, and well, this G1, G0 forms a groupoid. So we have the source and the target, and they give us the structure maps of the groupoid. Okay, so this is a groupoid of principal G bundles for a discrete group. And we can consider a particular example. So assume that our base manifold is just the circle. Then, of course, such a groupoid is huge. We have a lot of two-sheeted covers over S1. But we have very few up to an isomorphism. So define a subgroupoid whose objects are given by, so we have two objects. One of these objects is a trivial two-sheet cover. So we just take two disjoint copies of S1 and we projected the same thing. And the other is a non-trivial two-sheeted cover, which corresponds to squaring the complex variable which parameterizes our circle. Then we can define four morphisms in this groupoid. So two morphisms are just identity morphisms. Two others are flips of the fiber of each of these covers. And as it turns out, the inclusion of this G prime into G is an equivalence. So we obtained a simple characterization of this groupoid up to an equivalence. And it's natural to think that we indeed classified all principal bundles, and we kept track of all automorphisms. So it's natural to think that the answer to our problem are not just presheafs valued in groupoids, or I mean this particular presheaf, but presheafs valued in groupoids up to an equivalence of groupoids. So in more highbrow terms, we can say that it should be a sheaf which is valued in a homotopic category of groupoids, where weak equivalences are given by equivalences of groupoids. And that's the basic premise of Python to higher structures. We map our manifolds not just into some category with isomorphisms. We map it into a category where we have also weak equivalences. And we can say that the values are the same up to a weak equivalence. So let's make it a bit more, I don't know, topological. So we have this functor of the classifying space of a groupoid. If we have a groupoid, it's obviously a category. And we can define a simplicial set denoted by BG as the set of morphisms. So in each degree, we have morphisms from the simplex category of dimension n, meaning that it's just this chain of n morphisms. Of n morphisms. And the structure maps are given by the obvious functors between such categories, which just reproduce the standard morphisms inside of the this large simplex category, which contains all of these categories. So we obtain a simplicial set, and an important note here is that we can actually do this not only for sets, but if we're enriched over some category, then we can still take morphisms and obtain something valued in simplicial objects in this category over which we're enriched. So that's a pretty general construction. We can take the classifying space of a groupoid. Okay. And this functor over classifying space has some nice properties. So first of all, it's homotopical. If we view the category of groupoids as a homotopical category, meaning that we have weak equivalences given by equivalences of groupoids. Then, if we have an equivalence between groupoids, it passes on to an equivalence between the corresponding simplicial sets. And so the answer to classification problem for discrete groups, at least, would be the following. We take the opposite category of manifolds, we map into the category of groupoids together with equivalences of groupoids using this construction which was described earlier. And then we apply the functor of the classifying space to obtain a simplicial set. And so the composition of these two functors gives us a simplicial presheaf on the category of manifolds. So we're sort of close to answering our problem, how to classify principal bundles. But we still don't track the connection because we restricted ourselves to discrete groups. So first of all, let's consider a few useful examples of groupoids. So assume that we have an action of a group on a set, or more generally of a group object on, of a group object in some category over, an action of a group object in some category on another object in this category. Then we can form a groupoid or groupoid object in the following manner. So we take the objects of this groupoid to be just this set S, an object S, and we can take the morphisms to be this product, G times S. Then we obviously have two structure maps, the source and the target. So the source just projects on the first, on the second coordinate. So if we have GS, oh, that's not a good notation. Okay, G alpha. If we take S of G alpha, then we just obtain alpha. And if we take the target of G alpha, we obtain the result of the action of G on alpha. And so we obtain a simplicial set, or more generally, a simplicial object, which is just the classifying space of this groupoid. Sorry for this inconvenient notation, but generally, when we take this classifying space, then our notation agrees with the simplicial gradient. So in degree 0, we still have S, and in degree 1, we have G times S, and then we have G times S, etc. So that's one example, which is quite useful. And in a sense, this construction provides us with a good quotient. So in general, if we just try to take the quotient in a naive set-theoretical sense, for example, for manifolds, we can obtain something quite bad. However, if we do this, and instead of, I don't know, some kind of an ugly topological space, which is not even a manifold anymore, we use this construction and obtain a simplicial sheaf on a manifold, on manifolds, then we obtain a good quotient which has some nice properties. For example, its de Rham complex is quite computable and stuff like that. Okay, so another important example is what is called a check groupoid. So assume that we have an open cover, then we can take the objects of this check groupoid to be the disjoint union of elements of this cover, and the morphisms in this groupoid are disjoint unions of intersections. Then we have two structure maps which correspond to inclusion in the first and second chord. So U intersected with V can be included in both U and V, and that's precisely our two maps. And this is an example of a groupoid which is not just the usual groupoid, meaning a groupoid of sets, but it's actually a groupoid in a category in which we're considering this cover. So instead of an open cover, we can consider, for example, a coverage in a category with pullbacks, and this will work just fine. So, for example, for manifolds, by taking this groupoid and then by taking its classifying object, we obtain a simplicial manifold. But it can be done in general. We will obtain some simplicial object in our category. And that's very important because such check groupoids and check simplicial objects or check complexes are an actual way to resolve objects in a category. So we replace our object in a category with yeah. Please ask a question. Yes. Oh, I can't hear you. Maybe I have something with my sound. Wait a moment. So in the simplest case, S is just a set. So so this thing here will be a simplicial set. But as I said earlier, we can actually do this in any category, well, meaningful category where G is a group object. So for example, S can be a manifold and G can be a Lie group. And then this will still work, and it will produce a simplicial, yeah, it will be actually a simplicial manifold. Even that. So it's not just some simplicial sheaf on manifolds, but it's actually a simplicial manifold. So it's in a sense it's a representable simplicial pre-sheaf, even a simplicial sheaf. I think, but S can be thought of as an element of what is the action? Okay, so maybe let's discuss it a bit more, because I understand that it can be quite confusing since I didn't specify anything at all. Okay. Okay, so assume that G is a group object in a category. What does it mean? Well, it's just the same thing as for usual groups. It means that we have a multiplication morphism. We have the unit. We have the inverse. And we have the coherence diagrams, which say that, well, it's a group. So the multiplication should be associative, the inverse should be right and left, the unit should act trivially by multiplication. So that's just the definition of a group object. Obviously, if we have a group object and we have another object in our category S, then we can define what is an action. So an action is just a morphism which is compatible with these structures, with these structure maps. So, so if we have G times G times s, then it doesn't matter if we first apply the action or we first apply the multiplication. We will still get the same thing. So, and well, other obvious conditions for an action. That, well, the only other condition that the unit acts trivial. So we just have some action in a category. Then, as I said before, we can form a groupoid. So in degree 0, we should have, and that would be, well, that would be a groupoid object inside of a category C. So in degree 0, we have S, and in degree 1, we have G times S. And if we unwind the definition, then it means that this classifying space of our groupoid works like that. So we have the source and the target map. Then we have the map which composes elements of the group. So it's a map from G times S. So the first map composes elements of the group. The second map, I think, just throws away one of the multipliers, and the first one. And the third one applies the action on this part. And this can be extended to this infinite chain of maps in two different directions. So obviously here we just map S into E times S and stuff like that. Or formally speaking, since we're working in an arbitrary category, so this map is just the product of T and ADS. And this obviously works in any category. So did I somewhat answer the question, or should I expand a bit more? Okay, let's assume that that was sufficient, but please correct me, because I obviously don't know if any of what I'm explaining is clear or not. Okay, but we described two examples of useful groupoids. Let's now try to solve our problem for arbitrary Lie groups. So we define this new groupoid of bundles with connections as a groupoid where objects are given by pairs consisting of a principal bundle and the connection on it, and morphisms are given by isomorphisms, which are covering the identity map on M and are pulling back the form the connection on D prime into our connection. So that's a nice groupoid. So very well and good. And now we want to discuss a bit more simplicial presheets, since they already naturally appeared as classifying objects for well, yeah, as classifying objects over our groupoids, well, of our pre-sheaves and even sheaves valued in groupoids. So first of all, let's define what is an M stock of our pre-sheaf on the category of manifolds, or simply show pre-sheaf in the category of manifolds. So this is specific to the category of manifolds, obviously, because we use this non-negative integer m, and we say that the M stock is just the colimit of the value of f on both of dimension m and radius r, which converge to zero, which converges to zero. So first, I need to make several comments. So in general, if we are working in an arbitrary model category, not in the category of simplicial sets, of course, here we should take the homotopical colimit, but simplicial sets have a very nice property. If we have a filtered colimit of simplicial sets, it's actually the homotopic colimit. So that allows us to drop this annoying hole at the beginning of colim and write it like this. And another thing which is quite understandable is that it's actually, we can actually call it an M stock. So we don't have various stocks for various spaces, because all manifolds are locally the same. And that's the essence of why we can define an M stock. And why it's specific to the category of manifolds, obviously, for schemes with the risky topology, we can do that. But for schemes with the tau topology, I guess we can do that, because the tau schemes with the tau topology are, yeah.
What is a BM of R?
That's just an M ball in RM. So it's just the set of all. It's an open ball with consisting of all points with modulus less than R. So it just thank you for the question. As I was explaining, it just it's just a manifestation of the fact that all manifolds are locally the same, and that's not a property that is shared by many categories of geometric objects. For example, schemes with the risky topology are not locally the same. However, schemes with the tau topology are locally the same, which is nice, and therefore we can define stocks there in this fashion. Well, I think maybe not, because I'm not sure that we have such a nice filtered system there, but I think maybe we do. No, I don't think, because we can't intersect them and obtain another open subset. So I don't think that this works in many categories, but thankfully for manifolds it does. And we can define local equivalences for simplicial pre-sheaves as such maps that they induce weak equivalence on stocks. So stocks are just simplicial sets, and weak equivalences of simplicial sets are, as we know, just the maps which induce isomorphisms on simplicial homotopic groups. And also we have a nice property in the category of manifolds with open covers, which in some sense can be called discrete descent. So we have this simplicial manifold given by the Czech groupoid, which looks like this. So we have U A0, which maps into U A0 A1. So that's just the intersection, which is then mapped into the triple intersection, and so on. And this is a simplicial manifold because each of the intersections is a manifold, and disjoint union of manifolds is also a manifold. So we have a simplicial manifold, and we can take a discrete simplicial presheaf, which corresponds to this. Sorry, not discrete. Sorry, not discrete, but the representable simplicial presheaf, which corresponds to this simplicial manifold. So its value on an arbitrary manifold is just the simplicial set, which we obtain if we map our manifold into each of the degrees of this simplicial manifold and apply the structure maps. So it's a representable simplicial presheaf on manifolds, and for a simplicial and for an arbitrary manifold X, for which this U was a cover, we have an equivalence. So this is, in a sense, it can be called a discrete descent, or the fact that if we have an open cover, then in the simplicial world, it still approximates our manifold. Okay, but that's just some technical property, nothing too interesting. But now we're ready to construct our classifying presheaf for bundles with connection. So we take this groupoid of bundles with connection, which we described earlier, and we just take the classifying simplicial presheaf, which corresponds to this groupoid. So I'm sorry, I keep calling it a groupoid, but actually appropriately it should be called a presheaf of groupoids. So this then is a simplicial presheaf because on each object we applied this functor B and we obtained a simplicial set. And as it turns out, this is a sheaf up to homotopy. So if we have a manifold X and we have an open cover U, then we have a weak equivalence between homotopy limit of the values of this simplicial presheaf on this representable presheaf. So if you recall, the condition that something is a sheaf is when we just drop this HO and we say that we truncate this diagram in degree 1. So we just take the 0 stage and the first stage. But that's the natural generalization of the notion of a sheaf. So we just replace the limit by homotopy limit, and we replace this one truncated simplicial set by non-truncated simplicial set. So we obtain this simplicial sheaf or homotopical simplicial sheaf. And we can construct the universal bundle over our classifying simplicial sheaf. And we construct it as follows. So we constructed from not just trivial principal bundles with connection, but from trivialized principal bundles, meaning that we additionally have a datum of the section which trivializes this bundle. So the objects of this presheaf on a manifold consists of triples, principal bundle, connection, and trivialization. And morphisms consist of such maps between principal bundles with connection so that they preserve this trivialization. So they preserve the connection because of this condition, and they also should preserve the trivialization. And then we say that the simplicial presheaf is the classifying space of this groupoid. Once again, I use notation and identify the classifying space of a groupoid or the nerve with the groupoid itself. Okay. So as it turns out, this classifying pre-sheaf, this universal bundle over the classifying pre-sheaf is weakly discrete. What does it mean? Well, it's equivalent to a discrete simplicial pre-sheaf. So first thing that we observe is that if we have a bundle with a trivialization, then if we are asking for automorphisms which preserve this trivialization and are automorphisms of this bundle with or without connection, doesn't matter, we don't have any non-trivial automorphisms, just because we fix the way this bundle splits into the product of G and M. So the condition of equivariance prohibits us from having non-trivial automorphisms. And this means that we have this equivalence. So since this pre-sheaf is rigid, we don't have non-trivial automorphisms. We have this equivalence with a discrete pre-sheaf, where this is a pre-sheaf which takes the following value on an arbitrary manifold. So we just take one forms valued in the Lie algebra of Lie group G. Oh, sorry. Yeah, it's too much. And how this equivalence works? Well, in one direction, we do the following. So if we have a trivialized principal bundle, then we just pull back this connection to one form on M valued in Lie algebra of the group G. So a pretty clear construction. And the opposite direction, we do the following. Given one form valued in this Lie algebra, we just map it into the sum of alpha and theta, where theta is as usual the Maurer-Cartan form on G, and alpha is the same form. And this works because the total space is a product. So if we take the sum of such forms, we obtain a form on the product, which trivially restricts to the Maurer-Cartan form on each fiber, because when we restrict, we just kill this this summand. Okay. So here is just some general things that I explained earlier in relation to Misha's question. So if we have a category C and we have a group object in this category, then for any object X, we can define an action of this group object on X if as a such morphism from G times X to X, that it preserves, that it satisfies the usual action axioms. But of course, we require this to make sense, so our category should have at least some products. Well, maybe not all, but at least the products in these diagrams.
Sorry,
okay.
could you move to the previous slide?
Yeah.
What is a delta?
Oh, delta. It just stands for discrete simplicial pre-sheaf. So a discrete simplicial pre-sheaf is a pre-sheaf where in each degree we have the same space, or the same pre-sheaf in this case, and all the structure maps, all the simplicial structure maps are identities. So that's just, yeah.
Thank you. Yeah. Could you move to the next slide?
Mm-hmm.
And here we have an action on objects and on morphisms. Yeah, or on objects only?
No,
on objects.
On objects, just on objects.
Okay.
Yeah, but it is somewhat related to action on morphisms, because if we specialize the situation to the actions in a category of pre-sheaves, then we can define an action of a group object inside of a category C. So here we should have group object in C. To an action on F. And that's a particular case of the previous construction. So we take the image, well, the value of the UNADA embedding on G, we obtain a group object in the category of pre-sheaves. And then we say that, well, our group acts on this pre-sheaf if this morphism satisfies axioms of the action, of an action. And it is equivalent by UNADA's lemma to the fact that for any object in the category C, this group acts on this set. So indeed, it can be interpreted as action of a group of morphisms. It has group structure because G is a group object on certain sets for each object. So I hope it somewhat clarifies your previous question. And of course, if we have such an action, we can define the quotient, this simplicial quotient of a.
Sorry.
Yeah.
Recall what is a C of X G?
Oh, that's just the set of morphisms, because X and G are both in the category C.
From X to G?
Yes, yes.
Okay.
And it is a group because we have a group structure on the target. So since home is covariant in the second argument, all the diagrams from the definition of the group object translate into the appropriate diagrams in the category of sets. Okay, so we can define this simplicial quotient, and that's quite nice. We can now take quotients of sheaves by group actions. That's remarkable. Okay, so now we want to construct another model for our pre-sheaf B delta G. So we once again start naively. We take this B, I don't know, B crazy trivial delta G as a pre-sheaf of trivializable G bundles on M. Not trivialized, but trivializable. But this idea fails miserably. It's not a sheaf. And for practically the same reasons as our example where we tried to classify all bundles with connection. It comes down to the fact that we can have a bundle which is trivializable over each element of an open cover, but is not trivializable over the whole space. So the issue is the same. Being trivializable is a global property, and it's quite hard to track global properties using just sheaves because sheaves track local properties. They're made to do that. So we need to somewhat amend this construction. And we do this by considering the following. So assume that we have two trivializations of a given principal bundle. Then these two trivializations can be moved from one to other using certain smooth function valued in the group G from our manifold M. So I think it's called a gauge transformation. Correct me if I'm wrong. But the idea is that we just shift a fiber a bit, and we obtain a certain smooth function from M to G. And these functions, just by the silly definition, live in the values of this representable pre-sheaf on M. But recalling our previous discussion about actions of groups on sheaves, we see that actually this is not so stupid of a fact, because it means that our group actually acts on these one forms valued in G. And we can even explicitly write down this action. So the action of G on one form alpha is given by the following. So we take the pullback of the Maurer-Cretan form G upper star, and we obtain the adjoint action of G minus 1 alpha. If our group is a matrix group, then we can interpret each element G as an element of, well, as a matrix which acts on our Lie algebra, and we can rewrite this adjoint action like this. But that's this works only for matrix groups, for example, not for I don't know simplectic group. So we have to be a bit careful here, but it's relatively unimportant. Okay, so now we're prepared to construct this classifying presheaf of, which is actually the homotopy sheaf of trivializable bundles. And we do this just by taking the quotient. So as we saw earlier, we can take simplicial quotients of presheaves by group actions. And that's exactly what we do. So we take this discrete simplicial presheaf, or even we can say that it's not important. We can consider it just a sheaf, and we take a simplicial quotient, we obtain a simplicial presheaf. And we have a morphism from this simplicial presheaf into this simplicial presheaf, which works like this. So we just take one form, and then we map it into the sum of alpha and the Maurer-Cretan form. And if we have a morphism, then we map it into the apparent correct morphism. So we just map alpha plus theta into alpha G plus theta. And it turns out that this is actually an equivalence. So the proof is based around the fact that to be an equivalence in the world of simplicial presheaf with this model structure, we needed to be an equivalence on open balls. And it is indeed an equivalence on open balls because over any open ball, any bundle trivializes. Well, it trivializes. So we have many trivializations, but actually it turns out that if we have automorphisms of trivial bundles, such of a trivial bundle over a ball, such that they map one form which belongs to one form valued in G to another one form, we have a bijection with automorphisms of this bundle that map this form into this form. So that means that our morphism psi is essentially, it's fully faithful. Yeah. So it's essentially surjective because any bundle trivializes, and it's fully faithful because we have this bijection between morphisms in in the two groupoids which define both this simplicial sets. So psi is a weak equivalence. Okay. Now for the last part of our construction, we need a universal form. And it's not that hard to construct. So if we have this presheaf, which consists of trivialized G bundles, we can consider a morphism here. So morphisms from here to here correspond to forms to forms valued in G on this presheaf. And this morphism corresponds to mapping this triplet into this pullback of a form. So a pretty natural way to define the morphism. And finally, we arrive to the goal of this classification business, and we can define. We already defined two simplicial presheafs, a principal bundle between them, and we can state that this is indeed a universal bundle. So if we have an arbitrary bundle with connection, then we have a unique classifying morphism which goes into this B nabla G and pulls back E double G into P and pulls back the universal form into our form, which we specified earlier. Okay. So that's great. We basically completed our tasks. Let's look at the proof of this fact. So how do we construct such a map F? Well, if we have a principal bundle, then we can consider a principal bundle over a principal bundle. So we take this P over M, we take another copy of P over M, and we pull back one copy along the other copy. And this bundle canonically has a section. So we just take such a diagonal map, and it is obviously a section. So we obtain a trivialized bundle over the space P. But actually, if we have any manifold M, then we can define a map from.
Sorry. Why we have a section?
Oh, well, just because we can map P into P into PP. So why is it a section? Well, because by construction.
The fiber is P also.
No, the fiber is still G because we pull back a G bundle.
Okay, and P and why diagonal lies in this P with tilt.
Oh yeah, well that's just by definition because the set of because P tilde by definition consists of
this is a pullback. Okay, this is pullback.
Yeah, right.
Of course, so okay. And could you recall what is a what is the intuition of G with nabla? What is a simplicial object?
Sorry, E nabla G or D nabla G?
G with upper nabla. In the previous slide.
Oh, okay, yeah. Thank you.
What is the intuition of this object?
So basically, that's just a groupoid which classifies bundles with connection. So we just say that objects are pairs E theta, and morphisms are maps which preserve our connection. So phi of
okay,
theta
but you said that this is some simplicial objects. Yes.
Yes, because we can define the classifying object of this simplicial object of this groupoid. Sorry, the classifying object of this groupoid or the nerve of this groupoid, and since we do it on each object, we obtain a simplicial pre-phi. So
okay.
B nabla G on M is just the nerve of G nabla M. That's the construction.
Okay, thank you.
Mm-hmm. Thank you so much for this question. So if we have this trivialized bundle over P, it is a zero simplex inside of this EGP. So I wrote it absolutely horrendously. Obviously, I mean it's a zero simplex. But this means that for any manifold M, we can define a morphism from the set of smooth maps from M to P into zero simplices of this thing here, which is given by this. And then we just need to apply the union dilemma to see that this definition of F gives us a map from X to B nabla G. So that's just the sketch of the proof, the general idea how this is supposed to work. Okay, so I think we're quite close to the conclusion. The final part of this talk is the way we can generalize Chern-Weil isomorphisms into this statement. So we actually have Chern-Weil isomorphisms for these simplicial presheaves. How this works? Well, first of all, we need de Rham complex, obviously. And for a simplicial presheaf on manifolds, we define the de Rham complex as the vector spaces of homotopy classes of maps from F to this universal complex, which is considered. So I should have probably written it like this. So we consider this presheaf, and we take the discrete simplicial presheaf associated to it. And we have the differential, which is induced from the differential on this presheaf. We obtain a chain complex over R. And since omega dot is discrete, we have the following description of this set of homotopy classes. It's actually a kernel of this, or an equalizer of these two maps, which are given just by applying omega m n to the structure maps of the simplicial presheaf. So since omega n is contravariant, they go in the opposite direction. And that's the way to describe the de Rham complex for an arbitrary simplicial presheaf. Okay. But actually, there is a way to describe de Rham complex in a very particular case, or a very particular simplicial presheaf in geometric terms. So if we have an action of a Lie group G on a sheaf F on a sheaf F on manifolds, then we can describe the de Rham complex of the quotient as the kernel of the following map. Well, or as an equalizer. And as it turns out, this coincides with the notion of basic differential forms, which comes from differential topology. So I will give the definition in a moment, but if you're familiar with that, then these are exactly the basic forms we're used to. So what are basic forms geometrically? We had already an algebraic description, but we can also have a geometric description. So assume for simplicity that the Lie group acts on a manifold. Then a form on this manifold is called basic if for any vector field which is induced by a vector in the Lie algebra of G. So we have a vector in the Lie algebra, and then we promote it to a vector field just along the orbit. And for any element G in our group, we have that the contraction of omega with this psi psi is 0, and that the action, the morphism induced by this action on the restriction of omega to this presheaf is just the same form omega. So this can make sense for presheafs as well. And very approximately, this means the following: that our forms are invariant. So basic forms are invariant with respect to action of G. And additionally, it means that their sort of their change is zero along the orbits. So or if you want to, this means that
sorry, A with upper star.
Okay, so A with upper star is the action of morphism of A, just A, is the action morphism from GF to into F. So A with upper star is a pullback of this form omega from F to G times F, and then we restrict it to the fiber, so to speak. So we take G small times F. It's just a fiber inside of this product. And then we require this to coincide with this form which we just pulled back. And so geometrically, it sort of means that these forms are concentrated on orthogonal plates to orbits of the action. Okay. So just tiny bit of algebra, and then we will be done. So what is a Kazoo complex of a vector space? Well, if we have a vector space over a field over even a ring, and then a Kazoo complex is a tensor product of the exterior algebra with the symmetric algebra, with a differential given by the following. So we take dv for v, which belongs to the first exterior power of v, which can be canonically identified with v, into v tilde, which is equal to v if we identify the first symmetric power of v with v. So we have this differential, and on elements of the first symmetric power, the differential is zero. And this complex is almost acyclic, meaning that it only has one-dimensional vector space as its cohomology in degree zero. So now we arrive to Chern-Weil isomorphisms in this in the context of simplicial sheaves. So assume that we take this simplicial sheaf, then its the RAM complex is isomorphic to the Kazoo complex on the dual of the Lie algebra. In particular, it means that this simplicial sheaf is acyclic. And similarly, the Durham complex of the classifying simplicial sheaf is equal to the invariance of the symmetric algebra on the dual of the Lie algebra with respect to action of G. So that's what usually is called the Chern-Weil isomorphism, that we can compute the cohomology of the classifying space as invariant polynomials on the Lie algebra. That's basically the idea of Chern-Weil theory, of Chern-Weil isomorphism. And for an arbitrary manifold, we have the following. So first of all, the Durham complex of this product, so we take the product of X with this sheaf, is equal to Durham complex of X valued in the Kazoo complex of the dual to the Lie algebra. And if we have a manifold with an action of a Lie group G, then the Durham complex of its quotient is equal to the basic cohomology inside of this complex. So we have this far-reaching generalization of usual facts from Chern-Weil theory, Why is it so great? Well, basically because if we would look at this space as a certain, I don't know, topological space, it can be insanely bad. So for example, using this result, we can take the quotient of S1 times S1 by S1, where, by R, where R acts on the torus as a subgroup with irrational slope. So it has everywhere dense orbit. And topologically, we will obtain something non-Hausdorff, insanely bad. But using this formalism of simplicial manifolds and pre-sheaves on simplicial pre-sheaves and manifolds, we obtain a well-behaved object for which we can explicitly write down the de Rham complex and give the description of the cohomology.
What are the restrictions of this action G on X?
None. There are no restrictions. It just should be smooth. That's the greatness of this approach. So you don't have to think about, I don't know, properness, closeness of orbits, nothing like that. Just
okay, and the object X this object this quotient is some category. Yeah, we think about it as some category with action.
So X is just a manifold, but the quotient is a simplicial pre-sheaf on manifolds.
Ah, okay.
Mm-hmm. We can even think, yeah.
So the construction you described, actually, there is a certain about Chernville. There is certain another construction in equivalent topology. So Borel construction, when you
that's the Borel construction. That's the Borel construction.
So now you are going to refine it to the case where you have connection. Yes.
Well, I mean, no, I'm not going to do that, but yeah, it's probably
just proceed.
Yeah. Okay. Anyway, so I wanted to just finish this recollection of the story with the following, I don't know, moral tale. That as we experienced, sheaves allow us to capture some geometric structures in a uniform way. For example, we can capture differential forms like that, and many other things. And we can define what are differential forms on some, for example, infinite dimensional manifolds using this technique. But as we saw next, sheaves are insufficient to capture finer geometric structures, for example, connections, or I don't know, for example, foliations on manifolds. And simplicial pre-sheaves allow us to do that. So the moral of the story is that by passing to higher Topoi, we allow ourselves more geometric freedom while still retaining all the power of calculations, as we saw earlier with Chernville isomorphisms. So I hope that this talk will motivate somewhat technical details that will come next, because I promised in my today's talk to explain something about Jardin's model structure and Dagger's paper, but unfortunately, the story about this particular application took so long that I don't have the time to recall all these facts about Jardin model structure. But I hope that this story at least motivates why we need these technicalities, why we need to study the local model structure on pre-sheaves, on spatial pre-sheaves. Basically, we need to do that because it allows us to do all this stuff with Cherny theory, with classifying geometric structures. So I guess it's time to finish my talk. Thank you so much for attending, and please inform me if you want to give a talk yourself. So I guess that we will meet this Friday for the continuation of the story, which involves local model structure and spatial pre-sheaves, and well, certain technicalities. Okay, thank you so much. I will stop the recording now.